This is a character on a Macintosh screen. It is a bitmap image at a resolution of 72 dots per inch. The LaserWriter 2 printer prints at a resolution of 300 dots per inch, about 4 times more than the image on the screen of the Macintosh. In order to print a higher resolution image such as this, the screen image must be converted into a 300 dpi image. Built into the Macintosh ROM is a very compact and fast set of graphic routines called QuickDraw. QuickDraw is more than a page description language, in that it provides a consistent software interface across a wide variety of applications and output devices. It is the unifying technology of the Macintosh and a primary source of Apple's competitive advantage. QuickDraw is used in the process of printing in all 3 printers. In the LaserWriter 2 SC, the process of printing is somewhat different from the others which use Postscript as a page description language. In the LaserWriter 2 SC, a screen object or character will be converted into a 300 dots per inch image by using QuickDraw. When dealing with fonts, QuickDraw uses the same standard font 4 times the size of the screen font. This conveniently makes the conversion to 300 dots per inch. If, however, a font 4 times the size is not available, QuickDraw uses an algorithm to scale any other available font to create the required dot density on the page. Such scaling creates distortions and a lower print quality. This, however, is improved through a text smoothing process. In the LaserWriter 2 SC, the printer resource resident in the Macintosh operating system sends the bitmap image directly to the page buffer in the printer. Because the image is a 300 dpi page, it uses a considerable amount of data. A SCSI connection makes it possible to transfer this large amount of data at high speed. Once the data is stored in the page buffer of the LaserWriter 2 SC, it is already described as a 300 dpi image, and it, therefore, requires little processing to transfer it directly to the hard copy page. This is the QuickDraw process of printing. The print controller in the LaserWriter 2 SC fundamentally does 2 things. It gathers the data into the page buffer and then manages the flow of data a bit at a time to the print engine. Postscript is the industry standard page description language used in the printing process of the LaserWriter 2 NT and the NTX. In this case, the object on the screen is first described in QuickDraw commands. From there, the printer resource for the NT or NTX resident in the operating system of the Macintosh converts the QuickDraw commands into a shortened form of Postscript commands. The Postscript commands require little data and are easily and quickly sent through the AppleTalk to the NT or the NTX print controllers. The Postscript commands are now converted into a 300 dpi image. The process is something like using a dictionary. In turn, each command which could be part of an image is translated by the Postscript print controllers into its 300 dpi equivalent and stored in the page buffer. From the page buffer, the process is the same as for the LaserWriter 2 SC print controller. Each bit in the page buffer is sent, one at a time, to the laser, which images the page. The Postscript print controllers do not store images as bitmaps. Instead, Postscript uses outline font technology to describe objects as several splines or outlines. These curves are stored as mathematical constructs that form the outline of the character. The Postscript print controller processes the curves to draw the character outline, and then it simply fills it in. This type of character definition offers several unique features. The sizes of the curves are easily reduced or enlarged to produce a clear, undistorted image of the character regardless of its size. Also, a single definition can specify the size of the character. Character definitions are simply stored in one point size and then scaled to size as required. This uses less memory than storing every possible point size. When the information for an entire page has been sent from the Macintosh to the printer, it is constructed into a bit-mapped image to be printed. In the print engine, a bit-mapped image is composed of approximately 6.8 million possible dot positions on the actual page to be printed. Each dot position has a dedicated place in memory, which will store only one thing, whether there is a dot or not at that position on the page. This dedicated page in memory is known as the page buffer. During printing, the data in each one of the dedicated places in the page buffer will be fed to the print control logic. Creating a light image on the photoconductive drum is accomplished with the aid of an extremely fine laser. The print control logic activates the diode laser to either turn it on when a dot is required or off when a dot is not required. When the diode laser is turned on to create a dot, a pulse of laser light is emitted. During printing, turning on and off may happen at several million times a second. The pulsed laser light is aligned by several lenses into a beam. The beam strikes a six-faced scanning mirror that rotates at constant speed. The light pulses are reflected off one of the rotating mirrors and through a lens. A horizontal mirror reflects the laser pulses down on top of the rotating organic photoconductive drum. As the six-faced mirror rotates, each mirror in turn scans the pulsed laser beam across the drum. The drum also rotates at constant speed, and so dots are laid on the drum in horizontal raster scan lines. The laser light is pulsed according to the pattern of dots required for the scan of the beam across the drum. The quality of the dot matrix image the laser creates is dependent on several things. It depends on the dot density, or the number of dots per inch. In this case, the LaserWriter 2 printers lay down 300 dots per inch, or DPI. This means that the distance between the centers of dots is 1/300th of an inch, both vertically and horizontally. Also, there is a constant relationship of the distance between dots to the dot size. In the LaserWriter 2 printers, the dot size is big enough to ensure that adjacent dots overlap. When a line of dots is required, the resolution of the line is considerably reduced as a result of the overlapping of dots. Also, due to the darker blacks made possible by the improved toner used in the LaserWriter 2 printers, the contrast between the black dots and the page is enhanced. The consistency of dot size and the accurate placement of dots on the page also contribute to better print quality in the LaserWriter 2 print engine. There are 6 steps in the xerographic process. Step 1, charging the drum. Here, the surface of the drum is given a uniform charge. This is done by rotating the drum under a corona wire to which a high voltage is applied. As the drum rotates, the wire lays a uniform charge on the drum's surface. Step 2, image formation. During printing, the charged surface is selectively exposed to a scanning laser light image, forming an invisible uncharged image on the drum surface. Step 3, development. A magnetic developing cylinder attracts a special dry developer known as toner to its surface. As the cylinder rotates, a blade ensures that the toner is applied evenly. The toner, which is charged, sticks to the uncharged image on the drum, effectively creating a visible toner image. Step 4, transferring. As the drum rotates, the paper and the drum move together. The toner on the drum is attracted off the drum and onto the paper by the charge from a transfer corona wire under the paper. Step 5. Fusing. The paper with its loose, unbonded toner image is now passed through rollers which use heat and pressure to fuse the toner into the paper to make a permanent image. Step 6. Cleaning the drum. The transfer of toner is never achieved completely. The drum must be cleaned before the next copy can be made. A soft plastic cleaning blade removes loose toner from the drum. The drum is now ready for the next page to be printed. To feed the paper through the engine, the paper pickup roller engages the top sheet of paper in the tray and feeds it to registration rollers. The registration rollers hold the paper until the correct time arrives to feed the paper to the rotating drum. This ensures the image is placed correctly on the drum. Once the image has been applied and fixed to the paper, it is delivered to the print tray. The paper delivery sensor senses the delivery of the paper. If the paper fails to clear the delivery sensor within a certain time, the printer will indicate a paper jam.